All right. Welcome back. Awesome. We're live. Let me just pull off some stuff here. Cool. Welcome. How you doing? I'm Agent Ultra. I'll be your host tonight on the stream. Where I do stuff. Oh, 1 second. Okay, there we go. I think we're good. Sound levels are good. All right, let's get going. All right, I gotta pull out chat. Make sure we're good. See y'all. What you're doing, what you're saying. Okay. I'm on the ball today. All right, cool. Yeah, so for those of you who are tuning in for the first time, welcome. How you doing? On this stream, I generally build stuff. And for the past few weeks, we've been learning how to do wave function collapse. I generally do most of my projects on this stream, I think almost all of them, but there's been a few exceptions. In the programming language Haskell, I'm sort of into functional programming. I do it at my day job, and I do it on my free time. And I started the stream largely because a lot of people say to me, well, you can't actually write software in Haskell. Like, it's just not a thing. Which I don't think is true. We built quite a few things on this stream. We built a few games. We built some libraries, like Replicant, which is a library that's up on Hackage. That is a logical replication client library for talking to Postgres databases. And stuff like that. So, yeah, you totally can. And now, these days, we just keep that train going and build more stuff and just have fun programming and learning and stuff. So that's what we're going to be doing today. We're going to be learning about wave function collapse. We're going to be moving into the propagate step, kind of the final piece of the wave function collapse puzzle. And then hopefully we can start generating some images and stuff and just seeing how it works. So I'm going to go to my project here. I'm going to bring up my editor. Yeah, we're going to get this ball rolling. Of course, on this stream, I am always open to backseat programming or questions, diversions, questions of any kind, anything like that. So if you want to if you want to ask a question about what you're seeing, the code, or if you have general Haskell questions, those are cool too. All good. And if you have, want to see, you want to show off your project. I like looking at your projects, checking things out, see what's going on. And just general stuff, what's it like working with Haskell, that kind of thing. All good too. Okay, so let's get into the code. We're going to go into source, algorithm, wave function collapse, kind of where we've just been dumping all the code. Quite a bit. We're 500 lines roughly, but, we're pretty, we use the lines, you know what I'm saying? So, what do we got to do now? We got to implement propagation. There's our general formula for the algorithm here, kind of main thing. Choose a cell with the lowest entropy, collapse it, picking a pattern from the possible patterns, collapse it down to one available pattern for that cell in the output grid. And then we got to propagate that choice of that cell out to the neighbors across the wave. Okay, that's actually going to be a pretty chunky bit of behavior there, but I think we can do it. All right. So, I have been using on this stream a guide that is like a tutorial and also like some code implementation in Rust as kind of a guide as we're doing this learning, which we may end up using a little bit more, but I'm going to try and take a stab at this and see if, and the propagate, if we can kind of pull together something like the propagate step. And then kind of compare to that implementation in the tutorial and see where we're at. We did take kind of a look at the kind of high-level description of the propagate step a couple of streams ago, so I'm gonna kind of go off of my memory off of that and see where we go from there. So, firstly, with these kinds of algorithms, backtracking type of things, the general approach I've seen used a lot is keeping a stack going. So I think that's the approach I'm going to try and take here. Right, so the stack is the... Take Dijkstra's algorithm, for example, when you're looking at pathfinding. Right. In Dijkstra's algorithm, when you're trying to do some pathfinding between 2 points, right, you're searching through, from your beginning point, the available cells are in the local neighborhood of that cell, and if they're passable, you add it. Those are possible paths towards your target cell. Now you only need to look at the ones that are in the direction of the target cell, so you can ignore the ones that go the opposite direction, right? And then you have to go from each of those neighbor cells and look at the neighbor cells of those neighbors, and those neighbors, and those neighbors, and those neighbors, so on and so forth, until you find a valid path to your target. And so a lot those kinds of algorithms, the way they work is you put those neighbor cells on a stack, right? And then you have a loop that ticks off the stack and also puts more items onto the stack as you go. And then once you reach a certain end condition, then you're done. In our case, we're going to be adding this. I think we should add the cell that we want to remove, that we just collapsed. Something like that. And then we're going to we're going to loop through that stack and propagate those things. Now, we could use a list as a stack, potentially. Pretty common thing to do. I'm just wondering if there's like a more specialized data structure for it. Like a list would work just fine, I think. We just need we would just need like one function on top of it, really. Stack type. Stack is going to be so overloaded here, it looks like. Yeah, look, this isn't related to Haskell stack. Yeah, something goes pop, push. And it's literally going to be a state over a list. Yeah. Yeah, I think we'll just implement our own. No problem. So we'll go to our wave state. And we'll implement that. There. Wave state, removal stack. This will be a list of removals. Cells to remove? Cells to propagate to? Maybe we'll call it propagate stack. We could put the coordinates in there. Okay, so when we initialize the wave state, we have to initialize that empty. Propagate stack. Empty list. Okay, good. So that's all that there. Nothing else really uses it, so I wouldn't expect any other type errors there. Then we'll build a little helper function for pushing and popping to this thing in our wave state. Push propagate. Ooh, that's gonna be weird. Push propagate. Pop. That's going to be a wave state. Sorry, wave state unit. And that's going to be an int. Thing off our stack. Maybe. That'll be maybe int. Alright. So when you push, you kind of just push into the, like, it pushes basically cons on the list. And popping is just taking the head, but we don't want to just use the head function because it's partial. So we'll do our best to just wrap that in a maybe there. And that'll give us our semantics there for our stack. Okay, so we need a value actually to push on here, and int. I'll call it push prop. Actually, hopefully that's clear enough. It's going to be internal to us, but we should still kind of... I don't want them to be hugely, like, you know, named. But at the same time, I want to be able to come back to this in a while and, like, understand what's happening here. So, push prop. Might be good enough. Okay, push V, it will just be modifying the state. Modify strict with a function. Where we have the wave state propagate stack is going to be equal to V const on to s.wave state propagate stack. S such that. Yeah. Simple enough. And then propagating is going to have to inspect the state. And we're going to get just that stack. Wave state propagate stack. And then we're going to check. If it's the empty list, then we return nothing. Otherwise, we have an element and some more. In which case, we're going to update the state. Such, and we're going to take the state such that the wave state propagate stack is going to be equal to x's, and then we're going to return x. Oh, just x. In this case, has to return nothing there. Well, and there's our push prop and pop prop. Maybe prop stack would be better. Okay. Let's commit that. We'll just do a little work in progress one. Propagate stack. Okay. So let's kind of let's maybe try diagram this a little bit. So when we go to collapse the cell, we're going to pick a particular pattern to collapse that cell to. My handy-dandy hand-drawn grid. You know it, you love it. It's super wonderful. Okay. So we're going to pick this one here. Okay. When we collapse this down to a particular value, right, we're going to pop this on, we're going to push this, what are we going to push onto this stack? Maybe what we need to push on the stack is the pattern we picked and at which location. Right, because what I'm thinking here is that when we pop off of that stack, right, we need to know, we're trying to propagate out the allowed, following the adjacency rules, which patterns we want to eliminate from these adjacent neighbors. Here, 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 and here. We have the adjacency rule map, right? And so when we pop this off, we get the location of the pattern, the tile index that or the pattern index that we picked, and the location that we picked it at. Then we can go to each of the neighbors from that location, so these yellow grids here, and we can look at the adjacency rules, and based on which ones are allowed to be next to this pink tile here, right, we can eliminate the possible tiles that can't be adjacent to the pink one from the set of possible tiles here. All right, I think that's how we can do that. All right, Right, and then, so once we've done that for this one, we might have to figure out how to update the adjacent ones to this one, because there could be a case where the remaining set of available tiles could eliminate other available tiles for these ones adjacent to this top one here. Right. Those one, that one, and that one. So we might want to add something, like we want to push more things to the stack after doing this here, so that as we're popping off of the stack here, we get all of the propagations that we need to do. And finish. And then we're done once we have nothing else to propagate out. Essentially when the stack is empty. So what to put on the stack is what we need to figure out here, I think. I don't think it's just the location. We also have to pick the pattern. The pattern index. That we know that much at least. So let's update that. Let's create a type for it. Kind of like we did for entropy cell, we'll create a little new type. Or remove, propagate. I still don't know what to really call it. Propagate. Propagate cell. And that's going to be a tuple of the index. And we'll keep the now let's make it a record. And we'll go propagate cell pattern index, pattern X. I think you can use shortcut names as long as you're consistent with them, which is what we've been doing here with index. So I'll call it X. That'll be our location there, and or sorry, pattern index is just an int, and then cell location or cell X in the grid. No, we're propagating out the pattern to remove. Right? Because when we go out from this pink, we choose this pink cell, right? We're saying to the neighboring cells, this is the pattern we picked. Remove it from the possible set of patterns you can pick based on the adjacency rules. Yeah. Now we're gonna have to do this for each direction as well, like the 4 directions. Okay, so propagate cell index the pattern. So this isn't propagate cell. This is like remove pattern. Right, it's almost like a command. I'm gonna call it propagate stack. I'm gonna do place string on that. Propagate stack will rename to remove pattern stack. And then we'll name this prop pattern. Yeah, we'll just use the full name there. Why not? Okay, so push pattern stack, pop pattern stack. No, not remove, pattern. Actually, remove would be better here. And then this will be not maybe int anymore, but remove pattern. And that needs to change there to be remove pattern. Okay, small little step. Let's just checkpoint there. Add remove pattern. Rename propagate stack. It's more like a, yeah, like a stack of commands to remove patterns from cells. Okay, so we need to seed this with our first remove pattern command. Generally, that's how you kick these sorts of things off. So we'll do that at in the collapse at here. Wave state remove pattern stack. And this will be, it should technically be empty when we go to collapse, I think. Yeah, because I think the idea of the propagate step is we're gonna, yeah, cycle through this. We're gonna chew through this stack until it's empty. So yeah. Remove pattern. And what are we going to tell this command here? Which pattern are we going to remove? The one we just picked. Just cell, collapsed cell. Where's the cell? So fix the pattern here in collapsed cell. Which has the pattern index we picked in it. We know it's going to be just. So. We could do a little naughty here. Because we know in a collapsed cell, that cell collapsed is going to be just pattern index. Nah, it's kind of gross, but yeah. I don't know, part of my brain is racing. Like, now I kind of want to separate out the concept of, like, a uncollapsed cell from a collapsed cell and have, like, two constructors. Just so that we can eliminate this here and have the pattern index in the collapsed one as a value, and then we don't have to have the maybe there. That would be super sweet. I'm going to put that on a to-do as a possible refactor step. That's done. That's been a while. Oh, hang on. No. There we go. What do we call that? Like potential cell and collapsed cell? The refactor idea would be to split cell, do a get it, or sum, where each constructor, not with one cell and collapsed cell constructors containing the data for each. I think they're pretty self-descriptive. So the idea would be to get rid of cell collapsed. Maybe I should put that in there so future me remembers. That's what it's for. Continuing on. So remove pattern here would then have to, so we get the collapsed cell, we get the collapsed pattern. That'd be a let binding. And we'll do a dirty here. Or that's collapsed cell dot cell collapsed. And that way we get the collapsed pattern here, and the index will be the cell X. Pop that over here, pattern stack. And So we initialize that there. Okay, so once we collapse, the next step will be to propagate. Which is here. So we will put that after all of this nonsense. That's going to be a state, wave state, unit. All right. Okay, so the general pattern for propagation going to be while propagate the removal stack, pattern removal stack is not empty. Pop the top. Okay. So now, when we pop that element off, we need to look at that cell location, get all of the cells in each direction. Alright, so all of those yellow boxes there in my little diagram here on the right. Alright, and then we gotta eliminate the pattern based on the adjacency rules. Now the question remains how to figure out so we could push each of those on to the stack. All right. We take the removal, we remove it, we've got to we get the pattern to remove and a cell index. And then we have to, for each direction, right? We can get the cell at that location in that direction from the index cell. I'm going to call it cell X plus direction. Hopefully we kind of understand what that means. That basically means like from this location plus this direction would mean like get this one here. And then for that one and then that one and then that one. So like maybe start with up, right, down, left. Right, and then with that cell, we need to eliminate the pattern from the set of possibilities using the Yeah, I'm going to say eliminate the pattern from the set possible patterns based on the adjacency rules. And then we need to look at how to get the next ones to put on the stack. Right, and then, well, we need to, and then set that cell. Maybe we don't get the cell, but, you know, like we modify the cell at, yeah. Okay, and then well, what's happening here? Right. Once we've, so if we think about like the Sudoku puzzle, right? Once we have a set of numbers we've picked here, we've like cut down the list of available numbers here. There are certain ones that don't make sense for its neighbors anymore. And those would essentially be the ones remaining, the ones that we would like to have remaining here would be the valid ones that would be one of the possible ones that could be next to the ones in the cell we just kind of reduced. So like the ones could be the cell, like, and I'm trying to think of the word that would best describe that. Almost, I think if we think about the adjacency, let's look at the adjacency list. Think about the adjacency list. It's kind of like either in the range or the domain of the rules. Or to borrow from the model checking realm. So in I don't know if you've ever heard about something called TLA Plus, but it's essentially a language you'd use. How do I put this? It's a way of like describing state machines, I guess, and the different transition rules that those state machines can have, amongst a bunch of other things that you can do. But those rules, called actions, have something called enabling conditions, which says you can, which tells the model check, like the model checker uses this to say, like, you, from this particular state, you could go here, here, or here. Right? And I think what we're describing with these little yellow lines here, out from this top one, that fancy little guy there. All right, this fancy little line here, which is getting hard to see. It's saying like the ones over here, the potential ones over here are enabled by the sets of ones here. Alright, and so if we choose ones here, that we reduce the set here, it might reduce the set of ones that are enabled here. Right? Because we removed some possible choices that show up in the adjacency rules. And so we could stick more removals on the stack with each of those pattern indices, or the enabling ones here, with the cell index being this yellow this yellow dot. And I think we could push those on the stack as potential pattern removals as well. Yeah. And then our loop would keep going through the stack until they're all chewed up and they're all done. And so there could be that there are none eventually. There are no more to remove, and so we're done propagating. I think that's what's happening. That's how that should be handled. Hopefully this will make sense in a moment once we start putting this into code. It's sort of like, to go back to the Dijkstra algorithm, like sort of like picking which spaces to add to the frontier stack of cells you could go to, where you're kind of eliminating potential cells based on whether they're passable or not. All right, we're going to be eliminating potential cells based on whether they show up in a particular position in our adjacency map. But we're going to have to do that for each direction in this thing. I have to get to that in a moment. I'm going to save that onto my stack. Okay, so we modify the cell at the index, eliminate the pattern. Not necessarily there, but that's cell index plus direction. Eliminate the pattern from the set of possible patterns based on the adjacency rules. For each direction again. Then we want to get the set of enabled cells based on the adjacency rules. All right, so for all of those, the adjacency rules are almost like are kind of like our state transition rules, and we want to see the set of enabled ones that are enabled by the one we're looking at, to the one we're looking at. And push those as removals through the pattern removal stack. And then finally, I think at the very end, because we reduced the size of the potential patterns for that cell, we have to update that cell's entropy. Update the cell's entropy cache and cache. Yeah. Right. When we reduce the size of the entropy, we have to update which... Oh, and if we update the entropy cache, then we need to insert that cell also into the heap. Heap list again, so that it gets picked as potential new lowest entropy cell. And then I think that's it. And then eventually, what else could happen here? Well, we could end up... I think we could also end up in contradiction here, too. If you think about it. So, for each... Or we could detect contradiction here. The set of enabled cells from the one we're looking at, if there aren't any, then we have a contradiction. We've broken the adjacency rules. Well, a kind of global property of the grid that we need to have hold true in every possible state of the wave propagation, in that the neighboring cells of every cell respect the adjacency rule map. So if there is no pattern to pick in the set of enabled cells, then... Or if the set of enabled cells is empty in a particular direction, then yeah, that would detect a contradiction. I don't think there is a way, from my understanding of the algorithm so far, what I've read about it, contradictions are not completely avoidable. The idea of picking entropy is supposed to avoid it more often than not. If we were to do this a little bit more naively about which cell to observe and pick and collapse, we may encounter contradictions more frequently. Hopefully that's supposed to reduce that. I don't know how we're going to handle that really yet, but I think that's where where things will pick up. So that's the kind of plan we're going to go for there. Okay. So we could check while the pattern is not empty. By pulling out the stack from the state. Remove pattern stack. Okay. And then we can... how are we going to do... Well, we can just recur on it. What do we do? Like if stack, if null, is it null? Then we're done. Else. For each direction, we have to do something. I don't think we need the value back from it. I don't want to hard code the... I think if we make... directions... If we make this an enum, we should be able to iterate over it. We put bounded in there as well. Good. Enum dot something. No. Going to add enum. Info enum. I'm gonna just get rid of my drawing here. Enum from. Data foo equals var baz buzz deriving enum bounded enum and show, and we go enum from second type of client. No, I just got to give a value. Our baz cause. What happens if I give it baz? Yeah, okay. So I can't get the whole set of them. Bounded gives me the ability to get the min bound and the max bound, so I could define a little helper function. Or I could probably make a foldable instance for our type there. That might be the way to go. Yeah, direction. And the foldable class, to implement that, we can just look at the info upload it. The minimal we have to implement is fold map and fold R. Old map. Yeah, it doesn't make a whole lot of sense. Yeah, because we can't map things in direction. Yeah. So... I'm just gonna do this. Let's not get super clever. Simple, easy, trivial. There. We back up to here. And we can just do here, get rid of that. Okay. For each of those directions, we're going to do some stuff. Let's make it... We'll call it eliminate. That's going to take a direction. Doesn't have enough information here. Yeah, we gotta pop first. So we're gonna get a removal from that. We're gonna pop first. Pop. Remove. And then we can case match on that. If it's nothing, then we can return here unit, because we know there's no more left in the stack. Otherwise, we have just the removal pattern X and cell X. That's nice. I like that. That's much better. Then we're going to do... we didn't call it removal. What did we call it? Pattern removal? Or remove pattern? Yeah, like a command. Yeah. Remove the pattern. Pattern X to cell X. So we're going to have to pass those in. Oh, we want to pass them into eliminate. I think because we need the cell X plus direction to get the cell index of the one we want to do the elimination on. We probably compute that before and passing into eliminate. So instead of taking direction, we can take the cell index directly and the pattern index. Call it pattern X? Or did I name it something inconsistent? I did. Ugh. Inconsistency is no good when you're using shorthands. Ugh. Okay, wow. That's okay. Remove cell X. Cell, base cell index, and Oops, let's do that here. And so then we can go remove cell X here. Then the pattern X there. And that should satisfy eliminate. Provided we can implement this function here. I'll grab my type errors. I'm gonna grab my variable none scope error. Pop that over here. And that's gonna be state, wave state. It's gonna be. It needs a direction. Now it's going to return an int. That's going to be a type error. Select selections on the DR item here. Yeah, okay. Push stack. Oh yeah, we got our fixed push stack here, so that's just going to take our type here. Remove. That should be happy again. Yeah, and then we got our hole back there. Eliminate. That's good. So let's go implement or direction. Path. Cell X, cell Y, and a direction up. There is a cool thing that I wish I should probably use more. Sandy wrote it initially. It's super cool, but so Agda does this awesome thing where if you have a sum type here in your type signature, in like an Agda program, you can just have a nice little hotkey that just case splits on that sum type and creates the different cases for your function. Haskell has that too in the form of a plugin for, although I don't think it might even be integrated now, in Haskell language server that can do this as well with a little code thing. Yeah, I should look into that, maybe getting that going. Anyways, we're gonna have to type it in here. Four cases. We got up, right, down, and left. So in the case of up, it's cell X and cell Y -1. In the case of right, it's cell X +1, cell Y. In the case of down, it's cell X, cell Y +1. And in the case of left, it's going to be cell X -1, cell Y. And these have to actually be modulo the width of our grid. So we're going to need that as well. Maybe it's the first argument. So in the case we're doing y here, so we won't need max x. We will need modulo max y. Where we're modifying x, we're going to need max x, but not max y. Max x. And the same thing. Y again. Like max x instead of max y. And your problem is different negative arguments. Let's see, 1, 2, 3, 1, 2, 3. Oops. There. Okay, cool. So then we gotta buff over here. We have to give that max value there for the grid width. And wave state. We have the grid. And the grid has the array, which has the bounds, which is the size. Which keeps its bounds, which is the size. Yeah, okay. Where do we want to put that? We can do that down here. Grid size. We do a grid size here. Okay, and we're going to get the grid. Alright, that's going to be something on grid. That's going to get grid cells. That's not even in scope. Grid. Get cells. Okay, let's just get cells. Get cells. And this should be array.bounds. Like that. Okay, sort of. We actually need a hole from this tuple, which is going to be the lowest tuple and the highest tuple. We only need the highest tuple. We just need the second element here. Boom. Okay, now we just need to eliminate. We also have to think about property testing this as well. And I think there's a good one here that we can do once we get this underway here. And yeah, the property test is essentially that, remember the adjacency rule thing I was mentioning earlier? So as you go through a propagation step, and you eliminate, you collapse one cell, and then you propagate the picked pattern out to the adjacent cells, and you keep propagating the collapse, and as you reduce the set of possible cells, right? At every point during this algorithm, there is a rule that has to hold for every cell in the output grid. And that is that two neighboring cells that have been collapsed must always respect the adjacency rules in the adjacency list. Right? The adjacency rules of the function that we came up with. Right. And so there might be a good way to specify that in a property test. As long as we'd have a way of walking the algorithm to a successor state somehow, like maybe one step at a time kind of thing. Or maybe if we just define a way to pass in our assumption into a version of propagate that can check that for us as it runs, but wouldn't be used in the proper algorithm. Or if we could just run this state function one step at a time. We might be able to do that. Anyways, something to think about in the back of our heads. Might even just write that down. We do a test for propagation. I'm going to call the adjacency rule property is held in all steps of the algorithm, barring potential contradictions. Right, because there's always the possibility for contradictions, in which case that rule wouldn't hold in that state if we ever got to it, but we also know we wouldn't want to progress from there anyway, so as long as it's not in a contradiction state, this rule should hold, and probably should be able to specify that, I think. Oops. I was moving my hands back to home row and accidentally hit some keys. Okie dokie. What are we doing for time? We're still good. For a little while, at least. Okay, so eliminate. So we have to be able to get the set of enabled cells from the one we're looking at. And we also have to update the cell state at this location to remove the pattern index. Remove the pattern index. Or remove the potential patterns from the set of possible patterns So I remove the patterns from the set of possible patterns. Or the pattern index based on the adjacency rules. And then through the enabled cell thing, the enabled set. Enabled patterns for each direction. Not enabled. Yeah, so we want to get this set of patterns that can't be possible neighbors. So enabled from the cell we're looking at. Okay, I had it flipped around in my head for some reason. So enabled means from the remaining patterns we have in this cell, in a neighboring direction, we pick those. No, we want to go from the neighboring direction, so the ones that are not enabled, that are not possible neighbors of the cell we're eliminating, and queue those for removal in the removal list. Not enabled patterns for the cells in each direction. Queue those or add them to the removal. Add those patterns, the pattern removal queue stack. Yeah, I think that's the way, my friends. Hello, Lin Thunke. Welcome to the stream. First time chat. Lovely to have you. Are you interested in wave function collapse in Haskell? Or do you already do Haskell programming and just want to see more? Okay, so let's focus on the first part. We know how to do that. Remove patterns, we'll set up possible patterns. We're gonna need the adjacency list. Are the adjacency rules? This argument. Yeah, that's the cell index we're eliminating. That's the pattern index. Okay, apparently I don't have the adjacency rules in the wave state. I have the frequency hints. Okay, which is gonna trigger a few things, but not a big deal. I'm gonna just comment this for a second. No, come on. Okay, for some reason, GHC's subprocess here is getting a little confused. No worries, I know what I'm looking for. I just added the field to wave state here, and there's some, there should be a warning about this. For some reason, my editor GHC process is getting a little confused about that. So we'll just add it in. We have generate adjacency rules. Which needs the list of patterns. This needs some instances. We can just derive those. So we need a list of patterns to get the adjacency rules. We get the list of patterns. Not grid, which initializes the grid. Map and pattern results. What if we get passed in your pattern result? Patterns? What's this? Could not deduce equal. What can't be equal? Pattern result A. Oh, we need the extend. So it can't deduce as A has an equality instance in pattern results, which we said we needed. I'm not sure we need the. I guess maybe we need to. Okay. Should have it now. Oh, pattern result pattern. That's better. Okay, good. Okay, if such initializes the wave state. That's good. Let's go back to eliminate. Comment. Boom. so now we have a hole with the adjacency rules in scope. That's great. Super. Okay. After we have the adjacency rules, and we have the pattern index, we should be able to update the cell. Remove those possibilities from that cell. So the adjacency rules. Maps. An adjacency key to a Boolean. And an adjacency key is pattern A, and a pattern B, and a direction. Which we have by allowed. Allowed is our function. I can check that. Okay. Okay, so in this hole, do we have the data we need? We have the adjacency rules. That's one part. We have one pattern index. That's the one that was picked for elimination. And we don't have a direction in scope. So we're going to need to get a direction in scope in order to fill this hole in. And then we get the other pattern index, the pattern index B, to do our allowed check for each of the potential patterns in the cell we're trying to eliminate from. I think that's how we would do that. So let's get the direction in scope. So we queue up for removal. Remove pattern. We say, hey, remove this pattern. We have a direction. I was thinking of we would add the direction to the command. And then we wouldn't... check the cell. Because we're using that direction already here to calculate the cell index we want to update with removal. So we need the opposite direction. That could get a little confusing. Right. Because the adjacency rule is like directional on the grid. It's positional, right? So if I draw out my little grid again here. Right. Add like one more here. Okay. Another one here. Alright, so we pick this cell here. And we want to be queuing up for removal. That pop under is going to get really annoying. The pattern that we picked for the pink cell in this, say, cell above it here. All right, so to pass that information for that removal onto our stack, we could compute this direction and the cell index of this yellow cell here, as we've been doing. But then the direction of the adjacency rule, right, might be like blue is allowed to be above pink. Right, that could be our rule. Blue can be up to pink. Alright, that would be allowed. And so this blue would be a pattern that we could keep in the set of possible patterns for this cell. And so if I push on the stack from here, the direction up, that would get put here, and that would be good. And then we would check the set of possible cells in this cell. Then pattern A would be our blue dot here. And then up. Right? And we should get pink. But we should also have the other rule that pink is allowed to be below or under or down from blue. Alright, so we have like kind of two ways of passing that onto the stack. I believe both of those rules should be in the adjacency rules based on how they're generated. So we could push onto the stack the opposite direction of the one that we hear, take like kind of the contra-positive view, saying that meaning we pick this rule here. Alright, so we pass in this is the tile pattern index we're picking from this cell that we picked, and then we collapsed it. And we're pushing onto the stack that we want to eliminate that pattern from this cell up here. And we can give the direction the opposite of up, which would be down. And then we should have this part of the rule here and be able to match pattern B using our allowed function to pick the ones that can remain. And then if they're not allowed, then we remove them. We filter them out, essentially. I can get a little tricky. Hopefully that's not too confusing for ya. Or me, more importantly. Okay, so that means we do need some direction on the remove pattern command. We need the pattern index, remove, propagate, spell, direction. Give me a direction. got, and the index. So. So this, I'm going to document this just so that I remember this for future me. So the cell pattern index is the pattern we collapsed cell 2 that we want to propagate out to neighbors. This one, the cell direction, is the direction called the contrapositive. I'll just call it the opposite. Let's not get fancy. Opposite direction of the adjacency rule. For the propagated. For the propagate cell pattern being propagated. Right, so that we get the formula, the rule partially apply, basically. We can test aloud. Hopefully that will make sense. And then this third one, the cell X, is the cell the index of the cell we're proposing to eliminate from. Oh my god. Okay, so let's go to our first use of remove pattern. Right, so remove pattern, we have the collapse pattern. That's the one in this current cell we just collapsed. The direction, we have to pick the opposite direction. Which means we would have to populate this with a list for each of the directions. I think we could just put them all the directions in there. Oh, then the cell X that we're passing this initial remove pattern is the pink cell's index. Maybe we should remove that. Calculate it and eliminate. So the command is, in this direction, remove this pattern. Okay. Okay, so then our initial stack state is, after collapsing a cell, yeah, remove the pattern, this pattern that we collapsed to, up, right, down, left. That makes sense. Okay, and then here in propagate, when we pop from the remove stack and our removal pattern, we get the pattern X and direction. And we eliminate. Yeah, so we can actually just recalculate cell X here in the propagate step, I suppose. Whatever that function was, LX4 direction. No, we do need the things. We need that value there in order to calculate that. Eliminate cell X, or the cell X for direction of cell X and VIR. I'll call it from cell X. Remove pattern. Go back up to you. Propagate cell X. This will be our int. The cell that issued this command. And this will be the direction of the cell to remove the pattern from the cell X. Propagate cell X. We'll need cell X in there. Okay, push. Remove pattern, that's fine. Pop, remove, that's fine. Okay, and then oh, it needs the grid size. Okay, and then remove cell X. That is what that is. Maybe eliminate cell X, cell index, the pattern index. We also need that direction. Yeah, so I think in this case, actually, I think that might actually remove out some of the logic here, free some up a little bit here. We still need the eliminate cell index. Right. I think we can actually get rid of all of this. And just pass the pattern in. To eliminate. That. Okay. So now we have the remove. When we propagate, we pop off one of these removal commands. I'll remove pattern, and then we eliminate. We call eliminate with that remove pattern. Now eliminate, and the remove pattern has the base cell index from which we collapsed, and the pattern we collapse that cell to. The index of the cell, pattern we picked for that cell, and the direction. And the direction will be the direction of from the propagate cell pattern X. Yeah. Right, the propagation direction. So the command is essentially like up Get my pencil here. Up. Here. Alright. Remove. That's the direction. Alright. Remove pink. And remove the pink one. The pink pattern. Alright, you get the cell index, the pink pattern, and the direction. And that should be enough to formulate the key for checking aloud on the set of possible patterns in that cell. So we can eliminate some. Then we could filter, essentially, the set of possible patterns for that cell. And then we can update that cell state. I'm just noticing this is all kind of messed up. That's fine, we'll fix it. Anywho, let's continue on the path. Okay, so once we have the command at the eliminate step, we should be able to modify the cell. So I'm going to need some kind of modify cell function. Modify at, do I have that? Okay. I don't, okay, cool. Alright, modify cell at. We'll take the index. Cell explore direction. And that will be the propagate. Well, that needs the grid width as well, too. Propagate cell X and propagate cell direction. Oh, we can get this grid size, and that's not a problem. Should be able to fill that hole in. So modify cell at, then we get the cell, a function, which takes the cell and does whatever modifications we want to do to the cell. And the modify cell at will put that back in the grid. Modified cell back in the grid at the location. So we want to return the cell such that the possibilities are eliminated. Cell possibilities. We want to turn, based on the adjacency rule set and all that stuff that we have from the command, we want to turn these to false. Whatever ones match. Or do not match allowed. We have to be careful where we put the pattern A pattern B in allowed. And take the opposite direction, I think. So let's do that. Cell possibilities equals something. And data.array. Now we can do a big accumulating function Potential value, no, not quite. We might be able to do with our little array update function here. Something like that. So we'd have cell possibilities updated with something, which will be an association list that we'll have to fill in here. And provided we can do that, and then that should fill that in. So this hole here, get the wave state grid. Now we can let the grid size. We get cells from the grid. Then we get the array dot bounds, and we take the second of that. That might not be quite right. For some reason I'm thinking this. The second value is there. Is that inclusive in bounds? I think it's inclusive in bounds. In which case, when we modulo the indices, when we go to get the neighbors, be careful with that. That it's the Salix for direction function. Yeah, because if it's inclusive, then we want the cell. We want those to be the values of that we pass into from cell grid to be incremented by 1 if they're inclusive. Think. Let's just do a quick little test of the REPL. Right. So if my array bounds are like 0, 0 to 13, 13, it's inclusive, the 13 there. And so if we take that 13 and modulo it by 13, we're going to get 0. Which would be good, actually. We do 14. Oh, then we get 14. Then we get 13. Oh, that would be bad. We want 14 to be 0. Yeah, so we do want it to be incremented by 1. Oops, sorry. Sorry, no, I'm doing this wrong. I got them flipped around. 13 should be the max. So we do 13, 13, that's 0. And 14, so we try to use 14, then we go around to 1. We want that to be 0. Yeah, so we do want this to be incremented by 1. So that is 0, and then if we won't go 15, but if we tried to, it should be 1. Yeah. Okay. Cuckoo. So we do want to bimap incur. We want to bimap +1 on that. I don't have that because it comes from data dot bifunctor. Oh, maybe I don't need, maybe I just need that for a couple. It sells. What have I done? One function int to int. Can we do that map there? Put +1 there. Yeah, so I do need bimap, bifunctor. Maybe I'm just thinking the wrong function. It's not bimap. Yeah, bimap takes functions for each size of the bifunctor. Okay, whatever. It's a little redundant to have to say +1, +1. I think we can actually, maybe we can also lift it to just the one function over both fields. Oops. Yeah, okay. Oh, there's probably a shorter way of writing that. Okay. So that gives us the grid size to pass in here, grid size. And that will get appropriate cell. We just have to, as long as we can implement modify cell app. And this whole. But we are way over time. Okay, we'll put an empty list there. We'll have to implement modify cell at here. Leave it undefined. Take this. That. And stay with that. Okay, and then we could do parse error. I don't know. That's fine. Okay, a bunch of stuff to clean up, but yeah. Alright. Yep. Okay, bunch of stuff to clean up. Okay, so pushing this in this state is going to be breaking things. So, mark this work in progress, add elimination. Okay, do we want to push this up just yet? It's not quite done. So I'm gonna leave this local. Yeah, we're gonna leave this local for now, and then we'll try and wrap this up next week, and we'll push it up then once we have it implemented fully without all these errors and incompleteness. Okay, that's what we'll do. Add that. No. Leave that to do. Add another to do. Finish elimination. Save that. To do. Okay. Cool. Well, that was quite a lot, but I think we're getting really close, and we'll be able to finish this probably next week, and start. Maybe we'll do some of the refactoring, some of the property testing, and we should be able to start seeing some of the output of this algorithm real soon. I think we're gonna get real close to having the kind of pure version of it, and then from there. Basically, the plan would be, if the stream's interested, we could do like some analysis of the performance of our pure version. If it's not satisfactory, we could try doing a more optimized one with some mutable arrays and stuff like that. Or we can move on to a different project if we want to see some other stuff that you can do with Haskell and what have you. So, if you're interested in following along on what I'm up to and make some of these suggestions, you've got a couple of options. If you go to types.pl /Agent Ultra, I'm on Mastodon there, on the types.pl server. I'm Agent Ultra. There's links to all my socials and stuff. You can also post a little message to me, a toot or whatever they call them, and let me know what you think. Sometimes I post polls about stuff you want to see and all this kind of sort of stuff here. And you can also go to the link above my head that goes to declarative.tv, a cool little website with a Discord link to a Discord server where there's a channel for this stream. And you can chat with me between streams there, talk about your projects, post your questions, polls, and all that sort of stuff too about some of the projects you want to see. And yeah, all the code for this, although we haven't pushed up yet because we're kind of in the middle of it, but all the code for this is on GitHub. If you want to go check it out there. I'm Agent Ultra on there as well, and this is wave function collapse. So I'll post that in stream for you. And you can check it out there as well. Okay, and follow along, star, like, port, whatever you want to do. It's all good. Yeah, that's about all I got for this week. So thanks again for watching. I'm Agent Ultra. I usually do these streams once a week on Tuesdays. So if you're on Twitch and you have your notifications set up, give us a follow. You'll get notified when I go online. Sometimes I do streams ad hoc. Rarely, but once in a while it happens. And of course, if you go to my types.pl and you check out my YouTube channel there, you got a link there. If you follow my YouTube channel, like and subscribe there as well. Give us a little thumbs up because that helps a little bit. And yeah, I'll see you next week, hopefully. May your types always check. May your monads always be free. I said that in reverse, but let's be carefree and have some fun. Happy hacking out there. Take it easy. End of stream.